Hello friends, continuing with the topic of Ohm's law, today we take up preliminaries part 2, in which we will take up the terms like drift, 7th relaxation time, 8th drift velocity, 9th mobility, 10th relation between current flowing and drift velocity, 11th relation between current density and drift velocity. 6th drift, the net charge displacement in a definite direction under the action of applied electric field is known as drift. I repeat, the net charge displacement in a definite direction under the action of applied electric field is known as drift. When electrons acquire directed motion under the action of applied electric field, electrons do not move from end B to end A easily following straight path, but undergo collision with atoms and ions of the lattice of conductor and follow zigzag path in going from one end B to end A of the conductor. That is, electrons drift through the body of the conductor. Now look at the diagram. Here is an electron. It doesn't go straight from end B to end A, but follows zigzag path. It means it is drifting from end B to end A. Now, acceleration of electrons through conductor is not uniform. Acceleration of electrons through conductor is not uniform, but acceleration between two consecutive collisions is uniform. So here acceleration is uniform, but it is not uniform through the conductor itself. Okay. Assignment 3.1 continued. Question number 3. What is drift? Question number 4. Whether path followed by electron is A, zigzag, or B, straight. Question number 5. Whether acceleration between two consecutive collisions is A, uniform, B, non-uniform. So you answer these questions on the basis of the text that you have learnt. We have to understand is the relaxation time. What is relaxation time? Let us try to understand it. The time duration between two consecutive collisions is called as a relaxation time. Relaxation time is different for different collisions. Therefore, average relaxation time is calculated and denoted by tau average AVE. Therefore, average acceleration of an electron through the conductor, say A AVE, is equal to Vd by tau AVE, where Vd is drift velocity of electrons. AAV is average acceleration of electrons and TAV is average relaxation time of electrons. 8. Drift velocity. Let us define drift velocity. The average velocity acquired by the electrons under the action of applied electric field is defined as drift velocity. I repeat, the average velocity acquired by the electrons under the action of applied electric field is defined as drift velocity, mathematically expressed as A average equal to Vd by tau average, where A average is acceleration, average acceleration, Vd is drift velocity of electrons, tau average is relaxation time. Or we can write from this equation Vd is equal to A average into tau average. A average into tau average. And A average is replaced by F by m because according to Newton's second law of motion, acceleration is force divided by mass. So we replace here A average by F by m and tau average as it is. Or we can write it as write F as E small e into capital E, because it is the force experienced by the electron under the action of applied electric field E. So we replace F by small e into capital E divided by m as it is and tau average as it is. So drift velocity is equal to small e into capital E divided by m into tau average. That is the charge on an electron multiplied by electric field divided by mass of electron into relaxation time, average relaxation time. So this gives us the average velocity acquired by electrons under the action of applied electric field. Okay. 9. Mobility of electrons. Definition. Drift velocity acquired per unit applied electric field is defined as mobility of electrons. I repeat, drift velocity acquired per unit electric field is defined as mobility of electrons, mathematically expressed as mu e is equal to Vd by E, where Vd is drift velocity of electrons, E is applied electric field. Mu E is mobility of electrons. SI unit. For drift velocity we have meter per second, and for electric field we have volt per meter. On simplification we have meter square per second per volt. Therefore, SI unit of mobility is meter square per second per volt. Assignment 3.1 continued. Question number 6. Define the following terms. Number 1, relaxation time. Number 2, drift velocity. Number 3, mobility of charge carriers. Write its SI unit also. 10th. Relation between flowing electric current and drift velocity. I is equal to NEVDA. Now flowing electric current and drift velocity are related as I is equal to NEVDA, where N is number density of electrons, E is charge on an electron, Vd is drift velocity of electron, and A is area of cross section of conductor. Now we are to derive this relation. I is equal to NEVDA. So let us first develop physical situation. Consider a metallic conductor XY of length L. This is length L. This is conductor XY. Connected across a source of EMF B dash having potential difference V volts as shown in diagram. Now the electric field applied would be, say, E is equal to V by L. Let us mark it as equation 1, and direction would be from X to Y. I repeat, the electric field applied would be, say, E is equal to V by L, and direction would be from X to Y. Okay. Now in the second step we consider small length element traversed by the electron. Let Vd be the drift velocity of electrons acquired under the action of applied electric field. Then small length dl traversed by the electron in small time dt is say dl is equal to Vd into dt. Let us mark it as equation 2. Now in the third step, we are to consider small volume traversed by the electron in small time dt. Now if A be the area of cross section, A be the area of cross section of the conductor, then small volume dV crossed by electron in small time dt is say dV, that is equal to dl into A, or Vd into dt into A, because dl is equal to Vd into dt. So let us mark it as equation 3. Fourth, total number of electrons crossing this volume of conductor. If small n be the number density of electrons of the conductor, then total number of electrons crossing this small volume is say n is equal to small n into dV, or it is equal to n into Vd into dt into A. Let us mark it as equation 4. I repeat, capital N is equal to small n into dV, or it is equal to small n into Vd into dt into A, because dV is equal to Vd dt into A. Let us mark it as equation 4. Fifth, small charge flowing through this cross section of the conductor, say dq is equal to n into E, or it is equal to small n into Vd into dt into A into E, or dq is equal to small n into E into Vd into dt into A. Let us mark it as equation 5. Sixth, current flowing through the conductor, say I is equal to dq by dt. When we substitute the value of dq as ne Vd dt A, so dt in numerator and dt in denominator will cancel, and we are left with ne Vd into A. Or finally we write I is equal to ne Vd A. Let us mark it as equation 6. Now equation 6 is the required expression for current flowing through the conductor in terms of drift velocity. That is the relation between current flowing and drift velocity. Seventh, relationship between current density and drift velocity. Since current density is defined as the current flowing per unit area of cross section and is denoted by J equal to I by A. I repeat, the current flowing per unit area of cross section is defined as current density and is denoted by J is equal to I by A, where J is current density, I is current flowing through a conductor of area of cross section A. Therefore, from equation 6, we have J is equal to ne Vd. Let us mark it as equation 7. Okay, so this is how we have the relationship between current density and drift velocity. So we have seen two relations between relation between current flowing and drift velocity, and relationship between current density and drift velocity. Okay. Assignment 3.1 continued. Question number 7. The number density of conduction electrons in a copper conductor is estimated to be 9.5 into 10 raised to power 28 per meter cube. How long does an electron take to drift from one end of wire 3 meter long to its other end, given the area of cross section of the wire is 2.0 into 10 raised to power minus 6 meter square and it is carrying a current of 3.0 ampere. Question number 8. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 1.0 into 10 raised to the power minus 7 meter square, carrying a current of 15 ampere. Assume that each copper atom contributes roughly 1 conduction electron. The density of copper is 9.0 into 10 raised to the power 3 kg per meter cube, and its atomic mass is 63.5. Question number 9. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 2.5 into 10 raised to the power minus 7 meter square, carrying a current of 1.8 ampere. Assume the density of conduction electrons to be 9.5 into 10 raised to the power 28 per meter cube. Question number 10. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 1.0 into 10 raised to the power minus 7 meter square, carrying a current of 1.5 ampere. Assume the density of conduction electrons to be 9.5 into 10 raised to the power 28 per meter cube. Okay, thank you so much. Next time we'll take up part 3 of Ohm's law. Till then, goodbye.